Okay, thanks. Yeah, good morning, everyone. My name is Tim Draws. I'm a second-year PhD student at the Web Information Systems group at TU Delft, and I'm here to present our paper assessing viewpoint diversity in search results using ranking fairness metrics. And before I dive into what we actually did in the paper, I want to talk a little bit about what we mean by viewpoint diversity in search results and why we care about it. So here you can see a Google search that I recently conducted where I asked, should I be vegan? This is actually interesting also, I think, in the context of the keynote we had in the beginning today. And what Google returned me were basically, well, here I just show the top 7 results, and the first 5 results basically said, yes, you should be vegan, and the results number 6 and 7 said, no, you shouldn't be vegan. So this is to illustrate the point that for any sort of debated topic like that, veganism, who should I vote for, should we use nuclear energy, things like this, many of the search results that are returned will take some stance with respect to this debated topic. And of course, we have a position bias in search, which is the tendency for users to pay more attention and interact more with results that are ranked higher up. And research has shown that in the context of debated topics, this position bias goes so far that users can actually be nudged into accepting one or the other viewpoint. This has been dubbed the search engine manipulation effect before. It's of course not to say that this is necessarily a malicious intent on the side of the search engine, but what has been shown is that by simply rearranging the same set of search results, for example, people could be nudged into one or the other voting preference. So clearly, viewpoint diversity in search results is important to establish and important to maintain, but currently it's actually not possible to automatically assess viewpoint diversity in search results. So this was the question that sparked this paper. How can we quantify, how can we measure viewpoint diversity or a lack of it in a list of search results? And a very related field that we turn to here is the field of fair ranking. In fair ranking, usually what is measured is a ranking of people. So you can think of a ranking of job candidates, for example, and then we would want to look at whether, if I type in engineer in LinkedIn, whether, for example, male candidates are ranked systematically higher than female candidates. And usually these ranking fairness metrics evaluate statistical parity, which is in the context of fair ranking defined very similarly to its sort of general definition in fair machine learning, and namely that the protected attribute, such as a female, for example, in this case, should not influence a document's position in the ranking. And usually these ranking fairness metrics take on such a shape. So we have some function f that evaluates statistical parity iteratively for the top I documents in the ranking. This computation is discounted, and then finally the metric is normalized. So the question that we asked in our paper was, can we use, and if yes, how can we use these ranking fairness metrics to assess viewpoint diversity in search results? And the way we did that is we defined 2 different aims that a ranking assessor might have when aiming for viewpoint diversity in search results. And then based on these aims, we conducted 2 simulation studies in which we evaluated existing metrics, and also we proposed one novel metric. So how can we represent a viewpoint in a document? That's of course necessary given when trying to evaluate viewpoint diversity. I will illustrate this at the example of, right, should we all be vegan again? So if you imagine the scale from completely opposing veganism to strongly supporting it, basically, One taxonomy that one could apply here is this one, and this is the one we used in the paper. So here we assumed basically that every document could be classified into one of these 7 viewpoint categories. And the first aim that we thought about that a ranking assessor might have here is to protect one specific viewpoint or a group of viewpoints. So this is the case when, right, we are concerned that one group of viewpoints, in this case the opposing group of viewpoints, might not be heard enough. So we really want to make sure that this specific viewpoint or group of viewpoints is fairly represented in the ranking. So we define this group as the protected viewpoint, and all others combined as the non-protected viewpoint. And this is what we refer to in the paper as binomial viewpoint fairness. And this reflects basically a very classical application of fair ranking. And then the second aim that we thought about, okay, is what if you don't have a specific viewpoint that you are worried about, and instead you basically want to protect all viewpoints at the same time? So this is the case, right, when we want to basically make sure that all viewpoints are represented fairly without caring about one specific one. This is what we refer to in the paper as multinomial viewpoint fairness. We looked at a couple of metrics. Again, they take this sort of shape, at least the ones we looked at in the paper. And essentially, they all simply differ in the function f that evaluates statistical parity. For binomial viewpoint fairness, we considered a group of metrics that was proposed by Young and Stojanovic in 2017. You might know this paper. These are normalized discounted difference, where it's about the proportion of protected viewpoints in the ranking. Normalized discounted ratio looks at the ratio of protected and non-protected viewpoints, so it evaluates statistical parity that way. Normalized Kullback-Leibler divergence evaluates statistical parity in terms of comparing binomial distributions of the actual ranking and the optimal fair ranking. And then, because we found that none of these metrics were applicable to multinomial viewpoint fairness, we proposed a very similar metric where we use the Jensen-Shannon divergence as a distance function between basically 2 multinomial distributions that are defined over the 7 viewpoint categories. So how did we evaluate these metrics? As I said, we conducted 2 simulation studies. And the question here was, right, how do the metrics behave in different scenarios of viewpoint diversity? And to do that, we generated 3 different data sets, S1, S2, and S3. These data sets basically resembled corpora of documents that would be ranked in a ranking scenario. And all of these documents had basically viewpoint labels. And the sets differed only in the distribution of the viewpoint labels. So the set S1 was balanced in its distribution over the viewpoint labels, and the other 2 sets were slightly skewed towards the supporting viewpoints. And then per set, we basically created different rankings to simulate different levels of viewpoint diversity. How did we do that exactly? This was a weighted sampling procedure. So essentially, we just sampled from a set, for example, S1, without replacement to fill the individual ranks. And we did this in a weighted fashion. So there were 2 different weights that varied depending on how strong we wanted the ranking bias to be. So these weights could be exactly the same when ranking bias was 0 or viewpoint diversity was supposed to be high. And these weights could be vastly different, basically. So as I said, we created different rankings for each of the sets. For binomial viewpoint fairness, we assigned one of the sample weights to all the opposing viewpoints, and the other sample weights to the other viewpoints to simulate this binomial scenario. Multinomial viewpoint fairness was a bit harder to simulate, of course, because there are countless ways in which one or more viewpoints can be well, more or less advantaged in a ranking over others. So here we've just focused on one specific case where one random viewpoint gets a different treatment compared to all the others. Onto the results. So here we see the results for a normalized discounted difference. On the x-axis, you can see ranking bias. So basically, when ranking bias was extreme at -1 or 1, the protected viewpoint was treated as differently as possible, basically from the non-protected viewpoints. And when ranking bias was 0, they were treated the same. They were sampled with the same probability. And on the y-axis, we see the mean metric outcome. So at each step, we computed actually, because this involved sampling, we computed 1,000 rankings and computed the metric 1,000 times, and then took the average of that. So we see a couple of things. First of all, the metric essentially works. So for higher levels of ranking bias, we see a higher metric outcome. But what we see is that, for example, the metric is asymmetric. So when ranking bias is -1, this was the case when the protected viewpoint was advantaged in the ranking. The values go all up until 1. Whereas if the protected viewpoint was disadvantaged, the maximal values were lower. So we found that the metric is only really symmetric in a case where the underlying distribution of protected and non-protected viewpoints is completely balanced. So we see that as the proportion of protected viewpoints decreases, this is also the difference between the 3 sets, right? The metric outcome is a different one, and the metric becomes less sensitive to detect a ranking bias in favor of the non-protected viewpoints. For NDR and NDKL, this is a similar story. All the metrics have slightly different shapes. In NDR, this effect is actually very severe, so the values are much lower on the right side. But to summarize, essentially in their basic functionality, all the metrics work for this purpose. They just have to be carefully interpreted because, as we said, they are asymmetric. The proportion of protected viewpoints and also the direction of the ranking bias matter here. And which metric to use in the end depends on how strong the ranking bias is. So we can see, for example, that NDD is better at distinguishing lower levels of ranking bias, whereas NDKL is better at distinguishing stronger levels of ranking bias. Onto the multinomial viewpoint fairness results. This is a very similar story, so I'm not going to repeat the things that I just said. Essentially, the metric works. It's also asymmetric, similar to the binomial metrics. One crucial difference here is, though, that due to the different normalization that we had to apply here, the technical details of that are in the paper, the values are not directly comparable to the metric outcomes of the binomial viewpoint fairness metrics. So here, for example, we see that the maximum values are somewhere below 0.25 only, so they don't go up until 1. A quick discussion. So, as I said, the metrics essentially work, but they have to be interpreted carefully. Some kind of considerations have to be taken before assessing viewpoint diversity in search results. First of all, what is the underlying aim? Is it binomial or multinomial viewpoint fairness, or maybe something else where a different metric has to be used? How balanced are the data overall? Are they very skewed or very balanced? How strong is the ranking bias, and also what is the direction of the ranking bias? So, for example, is the protected viewpoint advantaged in the ranking or disadvantaged? All of these considerations matter when deciding on which metric to use and how to interpret it. Yeah, a little take-home message. Ranking fairness metrics, if interpreted correctly, can be used to assess viewpoint diversity in search results. And we think this is a very crucial step towards future work in which we can actually assess viewpoint diversity in real search results to actually get an idea of, okay, how viewpoint diverse are the search results that we get from, let's say, Google or Bing. And then also to align the metric outcomes with actual behavioral outcomes. As I said in the beginning, users are very affected by a lack of viewpoint diversity in search results, especially if they don't have a strong pre-existing opinion. So it would be interesting to see how strong a ranking bias or lack of viewpoint diversity has to be in order to cause these behavioral outcomes. Yeah, this concludes my talk. Thanks.
All right, many thanks for your presentation.